Last time we introduced this idea of restricted eigenvalue condition, which is a condition that gives you some slack in the restricted normal space property, and we saw that this is related to assuming some sort of a lower bound on the eigenvalues if the condition was not there. So the condition there makes it possible to satisfy something like this in high dimensions. So the so I'm going to go over the proof of the result that we had. It would become a little more clear where this comes from. So this is inspired by that argument about the restricted null space property, but we're not going to use that. So we can use this property to prove the result that we want directly. So the result that we had was let me maybe switch to this version. Yeah, okay, so it's a little bit better. So if you go back, so we want to analyze the these two problems, the L1 penalized regression and the constraint form, which is it just includes this penalty as a constraint instead of in the objective function. So there's the parameter lambda here, which is the regularization parameter. So there's this parameter, regularization parameter, and the corresponding parameter on the other problem. In the other problem is R. So generally, when you want to solve this, you would assume, for example, that, so we assume that y is x theta star plus some noise. So you'd assume that R is either the norm theta star 1, or at least R is bigger than or equal to theta star 1, so that theta star is feasible for 7. So you want to give yourself a chance that you actually recover theta star. So this is a little bit restrictive in practice because you don't know theta star. But if you allow R to be big enough, let's say you have some prior knowledge that this has to have a certain, at most like a certain L1 norm, then this is fine. This is sometimes called a local. It's not exactly this, but sometimes you even like impose more condition. Like you might want to solve this where theta minus theta star L1 is less than R. So you're very close to the truth. This is not like that. This is milder. Okay, so with these two problems, we have this result that if you solve the problem, either one of these problems under this noisy model, linear model, and if you assume that theta star is supported on S, the cardinality is less than small s, and X satisfies that RE condition with parameter kappa and 3 over subset S. So we remember in the RE condition, there is this cone here that is defined based on the support. So the support that we're using in that condition is the support of theta through theta star. So if we know that this holds over S, which contains the support of theta star, and S has the cardinality bounded by S, if I define Z to be X transpose W over N, any solution of the Lasso problem with lambda bigger than this quantity satisfies this bound, and a similar bound holds for the other problem if I take R star to be the L1 norm of theta star. So, and then as I mentioned, the optimal choice here, so optimal optimal choice. Choice of lambda is lambda equal to z infinity, and so this would be let's say equal to 3 over kappa root s. So here's 6 kappa root s z infinity. Okay, and you can see the dependence on s and z infinity and kappa are the same. Only the constants are different. Does this make sense? Questions about the setup? So kappa is what appears in the RE condition. If you go back, there's this lower bound here. So that controls this. Generally, kappa would be a constant for us. It's like 3. So this is a constant. The actual part is this part or this part. Sounds good? So why this is an interesting result? So if you recall Z infinity, the infinity norms of random vectors grow slowly in contrast to the Z2 norm. So we had we've seen some examples where if you have sub-Gaussian vector with IID coordinate or with independent coordinates with let's say second moment equal 1, then the L2 norm concentrates near the root of the dimension. But the L infinity generally is like root log the dimension. So that makes this quantity that appears here very desirable. Rather than the L2 norm, we have the L infinity norm. And so if you want to make it a little more precise, we can consider the setting where, let's say, the noise is Gaussian with variance sigma squared for each coordinate and independent, or basically IID. So W is WI, I from 1 to n, and WI is our IID. Normal 0 sigma squared. This is the standard regression assumption. And you can replace this with sub-Gaussian assumption, independent sub-Gaussian with sub-Gaussian standard bounded by sigma squared or sigma. Then we also assume this column normalization. So what this is saying is that if I look at the design matrix, so xj is the jth column. So jth column. So this is xj. So what we do is we're assuming that you normalize each column so that the like L2 norm divided by root n is at most some constant. So this is fairly benign. Usually in regression, you do some sort of a normalization. You do like centering and scaling. Basically by dividing all, so you can divide everything here if you want. You can divide y by a sufficiently large number so that effectively the columns of xj are upper bounded, that the norm is upper bounded by anything that you want. So this is mild. And then we recall that x transpose w over n, that's the definition of z. So, so why does this appear here? Maybe just give you some intuition. Anyone can give me some intuition why this vector matters, x transpose w over n. At least x transpose w, let's say.
X supposed to be
that's a good question. Yeah, orthogonal to the residuals, not the error there. So yeah, if you fit the regression, D is, so this is n by D. In the traditional, like classical setting where D is smaller than n, and you fit the regression, then you have the residual. The residual would be orthogonal to the column span of X. But here W is the true noise vector, true error. Right? So maybe any other suggestions? Right. So do you have like a simple idea? Think of the so let's say d is less than n, and x is an orthogonal design. Okay, orthogonal design. So what this means is that x transpose x. So x transpose x is the, so d by d. This is the Gram matrix. So if you recall, the ith entry would be the inner product of xi, xj. So this would be 0 if I is not equal to j. This can only happen if d is smaller than n. So these are the columns, right? So and let's say this is n. If I is equal to j, then x transpose x inverse over n would be I. So if you think of x as like these columns as 0 mean, this is like the sample covariance matrix. So you're assuming that basically the empirical covariance matrix is identity by this assumption. This part, I mean, you could do whatever you want, but let's simplify. So let's assume this. So assume that this holds. Then if you have y x trans, like x theta star plus w, what is a simple way to recover theta star? Great, yeah. So you multiply both sides by x transpose. That's basically you take the inner product with each column. That's how you usually do it. So this is that. Then I divide by 1 over n. Right, and so this gives me x transpose x over n with the identity. So it gives me theta star plus x transpose w over n. So you see, like the this guy is going to be unbiased for theta star, and then the error is this. And if you do the least squares, the usual OLS estimate, that's exactly this, because x transpose x is. So you can write OLS estimate as okay, theta hat. OLS is x transpose x inverse x transpose y, which is just, I can do x transpose x over n. Usually you normalize like this, x transpose y over n. And in this case, it would be like identity. This would be identity. So you get x transpose y over n. So that's really the OLS estimate. This is just saying you take the inner product of each column with y. And that would be your estimate of that coefficient, which is very natural if you think about it. Because the columns are orthogonal, you just take the inner product. So projection sort of separates along each coordinate. So basically, this is projecting y onto each one of the columns. So this vector matters, and it's not surprising that it matters in high dimensions as well. So this is like the effective noise on theta. Okay. So we have this z, but if you think about the usual OLS, if you do this, then let's say you want to look at theta star, theta hat minus theta star. Let's say squared. If you take the expectation, this would be like, because theta hat would be theta star plus that z. Remember, this is z. So what you get is this is going to be the expectation of z, L2 norm squared, which is bad in high dimensions. So what we're getting is, like, instead of the 2 norm, we're getting the L infinity norm using the L1 penalized regression, which is much better. Okay. Questions? This is like a brief little motivation. It's good to always think about the classical setting, and this result also holds in the classical setting. So there's no assumption of d being less necessarily bigger than n. So if that's the case, then the only thing that we have to control now is the z infinity. So the infinity norm here, this is a problem that you're going to show in your homework problems. And as you can see, the dependence on d is log d And then I have a dependence on sigma, which is natural because the noise is scaled by, that's the standard deviation of the noise. So if you rescale W with sigma, you expect the dependence of Z infinity on sigma be linear. And there's this slack that you have that allows you to control the probability here. Okay, so if I plug in the optimal value, lambda equal to Z infinity, oh, actually, I don't have to Z infinity, but if I let lambda be twice this, then I satisfy the condition, right? Because this is an upper bound. If I let lambda be twice, that's exactly this guy. So it's twice this. So then the lambda would be bigger than 2Z infinity. So I satisfy that condition. And then I can plug the lambda here. That's the, actually, like, including constant. So you have root S divided by K3 and lambda. So if you plug back in, you'd get something like that, okay? Then you can also take delta to be, let's say, if you want, you can take it to be root 2 log D over N. Then you can see from here that this would give me like 2 e to the negative n log D over N, and another 2 here. Sorry, there's a 2 there. Would be negative n2 log D over N, and then 1 over 2. So things cancel out, right? So you'd get, what do we get? So set delta to be that. 2, yeah, so you need 2 over D. So if D is really large, this probability is going to be small. So probability at least 1 minus 2 over D. And then you can absorb the constant, so you would get basically with probability at least 1 minus 2 over D, you'd get theta hat minus theta star. Less than or equal to, I'm going to absorb the constant. So I'm going to write something like this. You'd get C is this. I'm going to keep that there. So C sigma over kappa root S and then root log D over N. And I'm just going to combine the roots here. So you get root S log D over N. So that's the end result. Okay, so in high dimensions, this makes a lot of sense. So 2 over D would be very small. And so you'd get a nice result that, so these are constant. Let's say kappa is constant, C is constant, sigma you can think of it as constant. So what we have really is root S log D over N. Or you can just put sigma as well in case sigma goes to 0 or infinity. And then that's the probability. Okay, so as I mentioned, this is a very interesting result because if you think about the problem that I mentioned here, so if you do classical regression, but let's say I do it on the actual support, which is of size S. So the price that you pay is the size of the L2 norm of Z. And if you think about it, the L2 norm would be root S because you're in dimension S in that case. So what you would get is that this guy would be roughly, I would say Z tilde 2. This is the basically X sub S transpose W over N. So if I divide, so define it to be, let's say ZS, okay? So if I do regression on the known support, so I know the support in advance, I do this, then theta hat minus theta star would be roughly, the optimal would be like the OLS, so it would be roughly Z hat S2, and you know this is when it's going to be Gaussian, so this would be a scale like root N or sub-Gaussian, so root S, so this would be in RS. And then there's, sorry, there's some N as well. So there's a division by S, so you can figure this out easily. So this would be S over n because of the division by n here. So so ZS is XS transpose W over n. So it's XS divided by root n transpose W over root n. And this is like the assumption that we have here. So they're bounded by constant. So you can think of them as one. So they have unit norm. And then you can show that this scales like the L2 norm scales like root S. Do it as an exercise, actually sigma root S. So that's the more or less optimal thing that you can do. And what you get here is instead something which is very close, but you pay a price of root D. So that's the extra factor that you're paying because you don't know the support. And roughly speaking, this is the log of the cardinality of the search space, which is these choose S, so D to DS. Okay, so this gives you some intuition about what is sort of the best achievable case. It's always good to know what is best. It's hard to beat OLS when it works. And so this is like the oracle that knows the support can achieve this, and you're getting close to the oracle up to a log D factor. So this is an example where people got really excited about these high-dimensional problems because you're showing something under fairly mild condition. We'll see, for example, that this condition is satisfied for basically almost any Gaussian design. There's little like constraints on the covariance matrix even. And so if you do Gaussian high-dimensional regression with the proper choice of lambda, you can consistently recover. So this is a consistency result. So this goes, for this to go to 0, if you need n, let's say, much bigger than S log D. Or sometimes you write n bigger than or equal, like up to a constant S log D. So assuming, so let's do this. Yeah, actually we need n much bigger. So you need basically this to go to 0. It means n has to like grow faster than log D, S log D. But the key is that it can be n can be much smaller than D. Okay, it has to be bigger than S, but there is a big gap between S and D. Okay, so n can be much smaller than the ambient dimension. Some example that, yeah.
Is there any significance for like the reading theorem
You can definitely increase it. If you increase it, the condition becomes stronger. But you'll see in the proof, 3 comes in. I don't know if you can reduce it. There is a 3 that you pay. You can try to work out. Maybe you can change this constant here. Change that. It could be possible to change, for example, to most likely you could trade off some of these for that. Okay, but we'll see in the proof where it comes from. Are there other questions? Okay, so let's see how this is proved. So another point just to emphasize, this is an example where you prove something deterministically. So this result has no probability in it. So the lasso succeeds, or the constraint region succeeds, if this deterministic condition, these deterministic conditions hold. So lambda is bigger than the quantity. And then you verify, for example, that when you have stochastic noise, that for this to hold with high probability, lambda has to be bigger than this and that. Okay, so, and this holds, for example, with high probability for Gaussian design and so on and so forth. But it's good to separate the deterministic part from the random aspect. So it makes things more clear. So that's the deterministic part. This is like the application to the random Gaussian noise with fixed design. Later on, you can like make it random design, Gaussian random design, and then remove most of the conditions basically. Okay, so let's try to prove the theorem. So let's define this loss function. If you recall, so what I'm trying to do here, what I'm doing is I'm defining this to be L of theta. Okay, so the optimization problem is basically L theta plus lambda theta 1, or we're going to do the constrained version. So we're basically minimizing L theta over the L1 ball. And so let's go there. So let's try to simplify this objective function. So define delta to be theta minus theta star. And I'm just going to plug this in here. So let's say y is, y is x theta star plus w. So you plug this in here and combine the two terms that have x in them. So you get x theta minus theta star, which is delta. So this is delta. And then you expand. So if I expand, I get x theta delta norm squared minus inner product of twice inner product of x theta delta and w, and then 2's cancel out. So you get 1 over n here, plus norm of w squared, which is constant as a function of delta. Because I'm optimizing, I don't care about that part. So this is true. Then the next one is true. I'm just rearranging this. This is sort of like if you're a functional analyst, you would say x transpose is the adjoint of x. So I can move this to the other side. That's the definition of the adjoint. But if you don't want to be fancy, this is like x delta transpose w, which is delta transpose xw, which is just delta, right? Transpose x transpose w. Okay. So now we have our z here. So this part combined with this would give me z. So I have delta z, and then I have this part. So this is related to, you can see where that RE condition comes in. So to simplify, if I subtract L theta star, so L theta star corresponds to the case where delta is 0. So if I subtract L theta star, I remove the constant, basically the difference of L theta minus L theta star, that's the deviation in the loss, is given by this nice formula. Okay, so D is the delta is the direction that you move in. And so this is saying that if I say I have this, this is theta, let's say this is theta star. Actually, theta, this is the empirical loss, so theta star might not be minimizing. So let's do it properly. So these together will give me Z. So that's the loss. This could be theta star. This could be theta. And what we're saying is that you're controlling the difference in the loss in terms of the difference here. So delta would be that. This is L theta star, and this is L theta. Okay, and this, if you imagine this is unidimensional, like univariate, this is controlling the curvature. This is a linear term. This tells you how much curvature you have. If you move away, how much curved this is. And you can see that the RA condition are actually controlling the curvature here. So if this is really doesn't change much as you vary delta, it means that the curvature is small. So it's like this is almost flat. But if it varies a lot as you move delta, then the curvature is high. And we know that in high dimensions, there are directions in which this is really flat, and there are directions in which hopefully you have a curvature. And so the point is that what you're going to do is that we're going to look at the optimal solution. So for the optimal solution, I would get like L theta hat minus L theta star. I get 1 over 2n x delta hat. Delta hat is just theta hat minus theta star. And I would like this delta hat, the direction of the optimal solution, to be along the directions in which I have the curvature. If it's flat, it's going to be problematic. And you can see if this is going to be large, then we're going to have a very nice result. Because then I can say, whenever this part is small, then delta hat has to be a small. If the curvature is not there, if this is small, it could be like I have moved a lot without changing much. But if the curvature is high, whenever this is small, then the delta hat has to be small as well, so I have a control over the error. We'll see in the proof. So the next step is to use this so-called basic inequality. So theta hat is argmin L theta norm theta 1 is less than R. That's the constrained version. And we know that theta star is feasible because I assume that this is equal to theta star 1, L1. So we write down an inequality. So L of theta hat has to be less than or equal to L of theta star. This is sometimes referred to as basic inequality. So you start from something like that in analyzing an n estimator. And you can see, applying it to this, this side is negative, right? So what we're saying is, so let me put this here. This is hat, and I'm saying that this is negative, right? And so if you rearrange, it gives you this inequality. Okay. The next step is that's true. So theta star is not the optimal. Theta hat is the optimal, right? Theta star is the truth, right? Right. This is defined based on the observation. So you don't have the truth. So you optimize this. There's no reason why theta star has to satisfy this. But theta hat is by definition the minimizer, actually the minimizer of this. So theta hat is the optimal solution. So yeah, sorry? This is the minimizer of the loss by definition. This may or may not be. Usually it's not, right? So yeah, think of the, so let me tell you what happens. So what happens is that so let's say Z wasn't there. So Z, like there were, things were noiseless. Okay, so Z was 0. Okay, so when you try to minimize, hopefully you hope that the loss function of theta star is close to the loss function of theta hat. That's what you hope. Then you want to translate it to theta hat being close to theta star. So if the loss is flat, you could have, so this is my theta hat. So this is like minimizing the loss, but it's like loss is like this. It could be that I have so this is L of theta hat, and let's say this is L of theta star. So the difference is small, but if you translate it back to the deviation domain, the deviation is very large, could be very large. The more flat it gets, the wider this becomes. But if it's like highly curved, right? If this for the same deviation in the loss, I would have a much better control. In our case, any like curvature is good enough actually. The problem is where like in some directions this is like flat. So I could have like L theta hat minus L theta star is 0, but delta could be anywhere, like could be as large. So what you want is some curvature. The more curvature you have, the better. But in our case, some curvature is good enough. So that's the assumption that we make actually. So this is the curvature. So you're saying if this is small, this being small implies that delta is small to some degree. Okay. If this was 0, this could be small, like I could be in the kernel. I could move in the kernel, and this would be 0, but this side, like delta, could be like very big. The point is that we can't guarantee something like this in every direction. We impose this condition, and then the hope is that once I solve the L1 solution, like the problem, the solution belongs to this. If the solution belongs to this, then I can use this inequality. That's the main piece of the proof. That makes sense, sort of. If you you need a large curvature, yes. Yeah, so let's say if I want to argue correctly, this is like an empirical loss. As emphatically as your sample size gets close, like this is like Ln. Let me do this.
So that means this difference can be small if they attend somewhere to the point. But there are two directions. One direction is that the curvature is long. Another way that's the curvature is small. It's more flat.
Yes. Yeah. So the thing is, if I have, yeah, the plot that I had, right? Yes. It's a little hard to plot, but yeah. So we like this. Yeah, it will be flat in this direction, right? And so let's say if my sort of theta hat is somewhere here, theta hat is there, and it turns out that let's say theta star is in this direction, then it's good. I have some curvature in that direction. But if theta star lies here, right, it could be very far away, and it's still the losses are basically equal, right? Because I can move in this direction. The loss doesn't change, but I can be further, like further and further away from theta star, right? The reason why the loss gets close. So the thing is that these are dependent on the sample size. As the sample size grows, the loss converges to the population loss, and you hope that theta star is the minimizer of the population loss. So eventually, this is very close to the population loss. So the loss of this theta star, the empirical loss of theta star is very close to the empirical loss of the best possible, because this minimizes the population loss. This is minimizing the empirical loss, and the empirical loss is very close to the population loss. So this statistically, this is achievable. The loss, if the loss is good, so if your loss is calibrated so that, so asymptotically, empirical loss sort of goes to population loss. And so the minimum of the empirical loss, which is this, converges to the minimum of the population loss. This is going to converge to the population loss, minimum to population loss, and this is the minimum of the empirical loss. So they're going to be very close. But then you want to translate it to the input domain. That's where you need the curvature. Okay. Okay, good question. Any other? So we have this inequality. So at this point, I'm going to do the z infinity, bound this by z infinity. So you know this Holder inequality, xy is, so if you have looked at the matrix norm write-up that I had, there's this general inequality of Holder. So a special case where p is 1, q is infinity. These are the Holder pairs. So this is going to be bounded by Z infinity and L1 norm of this. Okay. So if you do like the Cauchy-Schwarz, you get L2 norm, and you can try, but the end result is that the L2 norm of Z appears. This approach allows you to like do this infinity norm here, and the L1 is sort of nice because you're optimizing already L1. So this is where the L1 really shines. So by assumption, we have this feasibility constraint, and if this is the definition of delta hat. So if I rearrange this a little bit, this is going to be theta star plus delta hat L1. Okay, that's the norm assumption. And this part of the argument is like the descent cone argument that we did. So this is theta hat star plus delta hat 1. I can decompose it into two pieces. Okay, theta star S plus delta hat S plus theta star S complement plus delta hat S complement L1. So this is going to be non-zero. This one is going to be 0. So this is 0 because S is the support of, or support of theta star belongs to S by assumption. Now we use the fact that the L1 is decomposable. So if you have a vector, you partition it into two pieces, the L1 norm of the entire vector is the sum of the L1 norm of the two pieces. That's not true, for example, for the L2 norm. So this is the so-called decomposability. So decomposability of L1 norm. So this tells me that theta star S plus delta hat S, that's this part, comes out, and then get delta hat S complement 1. So when I split into two pieces, this is the part that's in one index set and the part that's in the complement allow me to decompose like this. What is the next step? So if I plug back in, so the condition is that this guy is less than theta star 1. So if I plug this in here and rearrange, I keep delta hat S complement here, move the other term to the other side. Right? Oh, yes. So moving this term to the other side. And then this I can write as S here because this is just equal to theta star S. There is no S complement. Then I'm going to use the triangle inequality. By triangle inequality, this is going to be bounded by delta hat S1. So this is saying like A minus B absolute value is less than A minus B. You can remove the absolute values, but this is a form of the triangle inequality. Okay. If it's hard, you can just like think of it like this and then rearrange. It would be like this is bigger than the sum of the two. Oh, sorry, this is less than the sum of the two. Yeah. So it's a triangle inequality. So you can see that we showed, right? So feasibility of theta star implies that delta hat belongs to C1 S. That's the cone. So they're saying that the S complement part of like the L1 norm of the S complement part of delta hat is controlled by the L1 norm of this. That's the definition of the cone. Where do I have the cone? That's the cone. So with alpha equal 1, I showed that delta hat S complement is less than delta hat S L1. So this is the key part. So at the optimal solution, the difference to the truth lies in that cone. Okay, now I can apply my condition because I know this. There are two good things happen. I mean, first, I can apply the RE condition. The second is that if it's like that, then the L2 norm is much smaller than what you would expect. So if I want to, so you can see I have the L1 norm here. In general, if I want to bound the L1 norm by the L2 norm, I pay a price of root of the dimension. Okay, so if I just naively bound this by the L2 norm, how would I get inequality between this and the like upper bound in terms of the L2 norm? So the delta hat is in RD. So if I want to have this bounded by the L2 norm, what would be the factor that I have to put there? This is not a naive way of doing it because I could have done the usual Cauchy-Schwarz, but I had the Z infinity, let's say here. I like this. But now I want to connect it to the L2 norm because I can lower bound this by L2 norm of delta hat. How can I like relate this to that? Anyone knows this is like, so if you have a vector, the L1 norm is summation xi I from 1 to d. And the L2 norm is root summation I from 1 to d, right? Xi squared. So what is the relation here? You can use Cauchy-Schwarz. It's like 1 times this. If I do Cauchy-Schwarz, I get root d, yeah. Root d times that. Okay, so in general, sorry, this is, so the L1 norm is bounded. So there's this lower bound and then there's this upper bound, root d. So I'd pay root d here if I just do it naively. There would be a root d here, which I don't like. But because I'm in the cone, you can see that the L1 norm is, because it's just the sum of these two terms, is going to be bounded by twice delta hat S1. Okay, because the big part is controlled by the small part. And now this is in S-dimensional space. So this is going to be bounded by 2 root S, L2 norm S. Okay, and then I can further bound this by just the L2 norm of the entire thing. It should be not hard, like this is bounded by this. If you square this, it's just easy to see that the L2 norm of the full vector is an upper bound. So what I get is this very nice result that the delta hat 1. So this is one of the consequences of this being in the cone. It's as if this is the case where you have a vector who has like S non-zero coordinates. It behaves like a vector that has S non-zero coordinates. Although you're not saying that it has S non-zero coordinates. That's the first thing. So I can bound this side by root S. Let me finish it there. It's easier to do it there. So I have like detour. So I had 1 over 2n x delta hat squared is bounded by z infinity. Delta hat 1. So this is this side is going to be bounded by 1/2 kappa delta hat 2 squared. That's the RE condition. So we know that delta hat is in the cone, so I can apply this. And the other side is bounded by z infinity 2 root s and delta hat 2. Okay, so now this is squared. So if you rearrange, you get delta hat 2 less than 4 root s z infinity. And then you get delta hat 2. Okay. And then I can cancel one of the delta hat 2's. So I get delta hat 2. It's either 0, which is good, or if it's not 0, I divide. That would be my result. Okay. So you can see the curvature helps you connect this. This is from the loss to the deviation. And this other side is controlled nicely. And so magically you get this nice result. Sorry? Oh, yes, yes, yes. You're right. So this should be divided by kappa. Yes. So that's the result that we actually needed to prove. And going back to your question about the 3, so you can see 1 is enough for the constraint case. 3 we needed for the regularized version. But if you understand this, this is just the basic, the building block. And so this just shows you why it's working, basically. It forces the delta hat to be in the smaller set, and on the smaller set, good things happen. Okay, that the L1 norm is bounded by the L2 norm nicely, and the you have this curvature coming in. It's a fairly straightforward proof, but it's not simple to come up with it. You know, the first took people multiple attempts to get to this clean version. Sounds good. Okay, so let's do the regularized version now. So for the regularized version, we're minimizing this alternative objective function. So I start with the basic inequality again. The basic inequality says, so everything is feasible here. So theta star is feasible. The objective function for that has to be bigger than the objective function for theta hat. If you rearrange the part, the loss is controlled. So that's this is less than that. You had that. If you rearrange, you get these two terms. And then I move this to the other side. This is just the extra term that I had here. Okay, and the rest is similar to the constraint version. Now, so we had the feasibility assumption that allowed us to get this nice cone condition. Now I have to make this regularization sort of force that cone condition. So let's see how it does it. So this so this would be equal to theta star L1, and this one would be. So can you see that this is equal to the sum of the two? Right. The theta is basically theta star plus delta. So I break it into two pieces, theta star S plus delta S, that comes out like this. And then theta star S complement plus delta S complement. So theta star S complement is 0. So I just get that. So that's just the decomposability. So decomposability. 1. So now, if I look at the difference here, again, I'm using the triangle inequality, and then the second one comes here. Okay. So triangle inequality. So now I'm going to use this assumption, because lambda is bigger than 2z infinity. I can so basically multiply both sides of this by 2 lambda, right? So I get 2 lambda here. Just sorry. Why do I need 2 lambda? Yeah, okay, so there's a missing step here. So this is bounded by, I'm going to multiply both sides by lambda, right? And also multiply actually both sides of this by 2. So I'm going to remove this, 2 here, and then put a 2 here. Okay, so then 2 lambda is bounded by z infinity. Sorry. No, this is fine. So if you look at this, I'm just replacing it this with this one. Okay, and I'm just replacing. This is further upper bounded by 2 z infinity delta at 1. Okay, and I'm bounding this by lambda delta at 1. Okay, because 2 z infinity is bounded by, well, upper bounded by lambda. I'm bounding it like that, so that's this term. And this other term is 2 lambda is bounded by this, so I'm just going to do that. Okay. And I'm using this condition for the first term. Okay. Does this make sense? Sort of. So 2 lambda here, and then it's bounded by this. And then this term is again Holder's inequality, and then 2 z infinity is bounded by lambda. So I did that. Now, this is delta hat S1 plus delta hat S complement 1 by decomposability. So you get lambda delta at S1 plus 2 lambda delta at S1, I get 3 delta at S1. And then lambda delta at S complement minus 2 lambda delta at S complement, I get minus this. Okay. And at this point, I just drop the other side. So actually, not yet. So this is good. So this side is bigger than or equal to 0. This being bigger than or equal to 0 means this is bigger than or equal to 0. So this implies that delta hat S complement 1 is less than 3 delta hat S1. So you can see where 3 comes in. If this wasn't 2, this was some other constant, you'd get a different thing here. And that different thing would come up with, you can trade off basically. It's just not necessary, but you need something to have. You can try to see what other constants work. Okay, right. You need some sort of a cone condition still. It's okay if the constants here are different, but you want this to be negative. And so I have delta hat S complement L1 is bounded by 3 times. So this means that delta hat is in the C3 cone. Okay, and then the rest of the proof follows similarly. Because I have this, I actually can drop this now because this is a negative term. I can drop it. I get that this is bounded by lambda 3, this guy. Okay, so if you want, it's just 1 over n x delta hat. This is going to be bounded below by, I forgot what the condition was. Yeah, there is no 2. So this is going to be bounded by kappa delta hat 2. And it's going to be bounded by 3 lambda times delta hat S1, which is further bounded by root S delta hat S2. Maybe let me do it here. Okay, so that's Yeah, okay, so yeah, delta hat S1 is bounded by, or sorry, delta hat. This one is bounded by what? By 4 delta hat S1, right? Because of this condition. You split into 2 parts, and the bad part is controlled by this. So that means that actually I don't need that. I don't need this. So I already have the good part here, right? So this is just bounded by root S delta hat S2, which is further bounded by root S delta hat 2. Okay, so if you rearrange, you get delta hat 2 squared is less than 3 lambda. You said there was there a 2 there? Or? This seems fine. Sorry? 3? This is good? Okay. And then one of them cancels out, so you get delta hat 2 is less than 3 lambda k. Oh, there's a root S as well. Root S. That's what we wanted to prove. 3 lambda root S over kappa. The main point is that if lambda is large enough, larger than this, it forces you to be in the cone. So you need proper regularization. If lambda is small, this need not be the case, but once it's sufficiently large, you can go through the argument and see that would, that's where we used it. So you want to control this by lambda, and then you can just combine these with, yeah, like the regularization term. Okay, so that's what we proved. Yeah, that's what we need to prove. Yeah.
For the previous argument, for the going through, we also had said that delta hat was in the 3 time. I don't think we actually used it for this one. We only used it for the second group.
Yeah, you could just say delta like C1 here for the constraint one.
So it's not actually important for this one. It's in the 3 time.
Yes. Just because the theorem is stated for both, they put the more restrictive condition. But if you want, you can separate. You can say this with the C1. Yeah, for the constraint one, we don't need C3. And the 3 is not important, so you can, just to see it, you can try to go through the argument, change this, instead of assuming that 2z infinity is bounded by lambda, assume that like 2z infinity is bounded by some other constant times lambda, and see what happens. Okay. You need some conditions, but particular 3 is not important. Other questions? So this gives you a full proof of high dimensional result. And the only thing that, any questions? Maybe while I talk, you can think of questions. The only thing that we really haven't like properly investigated is the RE condition, whether it holds or not. And this is actually hard. So it's hard to verify this. I don't know a nice way of verifying in practice, actually. But not many people seem to care about this, actually, to verify it in practice. So, but you can, like, by some assumptions, the main point is that if you assume Gaussian or some other random design, then you can say this holds with high probability. Because verifying it in practice requires you to search for all possible, or that cone base. That cone is also non-convex. So you can't solve the optimization problem. So ideally, you want to solve an optimization problem. You can try to divide both sides by the norm of delta squared, and then try to minimize. So if I minimize 1 over n x delta squared divided by delta squared subject to delta in the cone. This is an optimization problem that can, in principle, solve. The minimum would give me the RE constant, but neither the objective nor the feasible region is nice. Both are non-convex. So whether you can solve this in practice is debatable. Okay, it's better than combinatorial optimization, but maybe not as much. So in the end, you might end up verifying it over all possible subsets. So then if that's the case, then you'd appreciate this result, which is a very interesting general result. So suppose you have a matrix, this is our design, and the design is anisotropic. Isotropic means the covariance is identity, yes.
This might be another question, but would you not like decompose the cone into like deconvex regions or something?
Deconvex regions. That's a very good point. In 2 dimensions, it's 2. The question is that what it would look like in d dimensions. Okay. Maybe you guys can think about it. Tell me. If it's exponential in d, then it's not going to be useful. But if the number of components is small, I can't visualize. But if you imagine, so it's like the L1 norm, that's an L1 norm. And for each coordinate, you can have like the signs, right? So 2 to the d possible like faces probably has that many, right? Yeah, it would have been nice if you could, right? Doesn't seem to be. Okay, so if you have an isotropic means the sigma is identity. So we have a Gaussian design, so the rows are IID. So each row is an IID draw from normal 0 sigma. Okay, so these are covariates. Anisotropic means that generally not identity. It could like covers the identity as well, but the nice thing is that it also covers non-identity. Then there exists constant C1 and C2 such that this inequality holds for all theta with probability this much. Okay, the thing is that this event, the entire event holds with this probability. The significance is that this is like a uniform result. This is saying that for all theta, this inequality holds. So there's an event which has high probability for which this inequality holds for all theta. To appreciate this, what it's saying is that, so this is lower bounded by something. This is the population version of this side. So if you square both sides, this is 1 over n we do it here. So theta hat. This guy is theta transpose x over n theta. This is like sigma hat, and this is actually sigma hat n because is it sigma hat n? Yeah, because the rows are 0 mean. This is really so think of the x as x1 transpose up to xn transpose. Then these are the rows. So x transpose would be x1 up to xn columns. So if you multiply this by, so multiply these 2 guys together, what you would get is x transpose x would be summation I from 1 to n, xi transpose. And so this is really 1 over n, and this is, so each coordinate is an IID draw. The expectation is, so if I divide this to be sigma hat, expectation of sigma hat is 1 over n summation I from 1 to n. Expectation xi transpose. And this is just sigma. Okay, so this is an unbiased estimator of sigma. It's the sample covariance matrix. Right. Sample covariance matrix. So this is saying this side is basically theta hat by theta transpose sigma and theta, and the other one is like root sigma theta squared, which is theta transpose root sigma theta, which is just theta transpose sigma theta. Okay, so this is like the population version of this. This one in general would satisfy an RE condition. So this is, you can assume that this is bounded by, say, gamma min sigma norm theta squared. This is reasonable because this is a population covariance matrix, like infinite sample size. So you can assume that the gamma min is, this is the smallest eigenvalue is bigger than 0. So the population version satisfies this. This, however, cannot satisfy it because it's a sum of a bunch of n terms, each of which is d by d. Okay, so this is rank deficient, so this has a lot of zeros, 0 eigenvalues. But the good news is that this is lower bounded by this minus some pen. So if you give me some slack, which is this part, so if you subtract this little bit here, then I have the inequality. Okay, and the good news is that for sparse vectors, this term is going to be much smaller than this. So this would be a multiple of this, smaller multiple of this, so you'd get the RE condition. So this one you'll verify in your homework problem. I'm not going to do it. It's very simple. So if you have this condition 9, then RE condition holds over C3S uniformly over all subsets of cardinality at most this much. So for any subset whose cardinality is bounded by this, it will hold, and this rho squared is just the maximum of the diagonal entries that appears here. So what this is saying is that if I call this little s, so you can see this is some constant dependent on and sigma treated as constant. So this is saying that if s is less than or equal to a constant, up to a constant n log d, or equivalently, if n is bigger than or equal to s log d, then we have the desired RE condition over all subsets of size s. So that's the result that I mentioned, that you could get this complexity for any covariance matrix without any correlation assumption. The only thing that you need is that this is not rank deficient. So this, for example, holds. Remember this matrix that we had, spike covariance matrix. You can see the diagonal is just 1. So rho squared is 1. Lambda min is 1 minus mu. We did the calculation. And so for any mu other than 1, this would be just some constant. And so the RE condition is verified for this. The other example is where you have this tall plates family. So it's like 1, 1, 1, 1. And then nu above and below diagonal, and then nu squared. So there's like covariance matrix of the stationary time series. So nu is less than 1, so it decays if you go away from the diagonal. This is saying if the distance between two elements is large enough, the covariance is small. So covariance of, let's say, AR processes, if you have seen time series. If that's the case, then you can show lambda min for this is like 1 minus mu squared, still bigger than 1, bigger than 0, and this is equal to 1. So we have this nice result. To get an intuition why this is, so if you just imagine that for sparse vectors, this is bounded by root s times the L2 norm, as I mentioned, rather than root d times the L2 norm. So if you assume that this is sparse, then this would be root s L2 norm. And you know that over this cone, the things look like sparse, right? So over this cone, the L1 norm would be like root s times the L2 norm. We did the calculation. And so you get root s here squared, you get s log d over n, and then L2 norm here. And then L2 norm here, sort of you can control sort of. You get lambda min minus S log D over N. And if this is small enough, smaller than lambda min. So just do the calculation. It's very simple. And we have questions. So next time I want to come and prove this. I'm going to post the proof. The proof is like the most difficult proof that we're going to do in this course. I usually debate whether I want to do it or not, but I'm going to do it. It's going to take probably the whole next lecture, but it's useful because it uses a lot of techniques. Okay. Thank you. See you next.